So 3.4 is called Eigenvalues and Eigenvectors. So I notice I have a lowercase here. That should be uppercase. Okay, so an eigenvalue of a matrix A is a scalar. So they usually use lambda. That's the Greek letter. There's probably no B there, lambda. There isn't, or there is? There is a B? Okay. Yeah, I don't know. That's how we say it anyway, lambda. So, yeah, if there's a B or not, I'm not sure. Okay, so it's a scalar lambda. So we just use that. That's just a letter chosen that they use usually when they're talking about eigenvalues, okay? So that doesn't mean anything special other than it's the letter they chose. With the property that A times the vector x is equal to lambda times the vector x. So I'll show you what that means in a minute. The vector x is called the eigenvector, and the set of all possible vectors that have this property is called the eigenspace. Okay, so an example, if I had a vector A, and this is an eigenvector, x is an eigenvector of A. So the question is, find the eigenvalue. So if we multiply A times x, we get so 1, 4 times 1, 1. So 1 times 1 plus 4 times 1. And then 2, 3, 2 times 1 plus 3 times 1. So this is 5 times 1, 1. So here we have A times x is equal to lambda times x. So you see that the 1, 1 and the 5 could be factored out, so we have A times x is equal to 5x. So lambda is equal to 5. Okay, so 5 would be the corresponding eigenvalue to the eigenvector 1, 1. All right, so just a second example along the same lines. If I give you A is 1053, and the question is going to say determine which of the following vectors are eigenvectors of A, and find the corresponding eigenvalues. Okay, so I've got more than A, B, C, D, but we'll do these ones first. Okay, so what do? We want to find whether it is an eigenvector, because not all vectors are eigenvectors. So we are going to multiply A times the vector. So A times the vector. And what we want to see is this a multiple of the vector 0, 1? So a multiple of 0, 1 would have to have 0 in that top spot, because any number times 0 is 0, and then, so any number is the second spot. So when we multiply this, what do we get? 1 times 0, and so 0. So far so good. And 0 plus 3. So what is the eigenvalue? What can we factor out of this vector so that it looks like that one? 3. So lambda equals 3. That's it. Now, later, after we finish this example, we're going to learn how to find them not given an eigenvector or an eigenvalue, and we have to find them both just from the matrix A. So that's what we're going to do. Okay, so is this one? So if we multiply, we get minus 2 plus 5, minus 10 plus 15. So we get minus 2, 3. Is that right? Okay, so is this an eigen, can we factor something out so that these are multiples of each other? Oh, 5, thank you. Thank you, yeah. Minus 10 plus 15 is 5, yeah. So they actually are the same. So what would the eigenvalue be? 1. Lambda equals 1. All right, so this is minus 2 plus 0. And then minus 5 times minus 2 is minus 10 plus 15. Okay. So this one, what are we going to get when we multiply by 0? 0. So just a note for this one, an eigenvector must be non-zero. Okay, so this is not. So an eigenvector, it has to have a value that's not zero. It could have, you know, if it could be a great big long vector if this was a bigger matrix, and they could have all zeros, but one number can't be. Yeah, so it has to have at least one non-zero number. Let's write it that way instead of be non-zero. We say if a matrix or a vector has one non-zero, one non-zero number, it is a non-zero vector. But that's also true. Okay, what about this one? So here we will get 4 plus 0 and 20 minus 15. Oh, minus 30, what am I doing? Take a couple days off and I'll, there we go. 1 again. So lambda equals 1. Now what do you notice about these two that we got lambda as 1 for? Look at them compared to each other, like this and this. Do you see they're a multiple of each other? And if I put any other multiple of these, they would also give us a 1. Okay, doesn't matter what it is. I could multiply this by 100 and that would still work and give us a 1. Okay, this one? So 1 plus 0 and 5 plus 3. No. Not an eigenvector. Not an eigenvector. okay, because it's not a multiple. And the last one, what do you think before we do it? Yes, because it actually follows which pattern? The same as A, 0 and a number. So any multiple of one that works will also work. And give you the same eigenvector, or eigenvalue. So this will be 0, and this will be minus 6. If we factor out a 3, we get the original vector back, so lambda equals 3. Okay. So in fact, a 2 by 2 matrix can only have, at most, 2 different eigenvectors or eigenvalues. All right, so a 3 by 3 can have at most 3. It can have less, but it can't have more. So, okay. So how to find eigenvalues, vectors, and the eigenspace. So there's sort of 3 things I could ask. Oh, I did. Good thing you guys are on the ball today. There we go. Okay, AX equals lambda x, so we start with that. Now, we're multiplying A is a square matrix, we know that, and X is a vector, so a column vector. And this isn't a matrix times a vector on the other side. But it does give us the same answer. Right? What is the size of A in general? So it could be a 2 by 2, it could be a 3 by 3, it's square. So we would say in general this is an n by n. And so what size would X have to be for it to be able to multiply? N, not 2, because whatever size this is, n by 1, because these middle ones have to match up, right? And lambda is a scalar, and x is an n by 1. So on this side we get an n by 1, right? Remember, these match so that the answer is n by 1, okay? So that's about the size. Now what if I moved the lambda x, or subtracted that from both sides? Whoops. So AX minus lambda x equals 0. Okay, so this is possible only if we change something. It's not possible right now, because to subtract matrices, they actually have to be the same size. The answer to this is the same size, and the answer to this is the same size. So as long as you do these separate, you would be able to subtract. They'd both be n by 1. Do you agree with that? But when you look at them, they're not the same size when you write it out. Okay, but if you did them separate, it would still work. So this is still okay. But what if I wanted to factor out the x? So both terms here have an x. And remember, with matrices, if the x is after or at the end of AX, you have to factor it out on the back. It has to be still after. So this would look like this. And now this is no longer okay. What's wrong with it? So lambda is what size? Right, it's just a number, 1 by 1 if you want. And this is an n by n. They're not the same size. So when you do this, there is actually a way to do it so that this is still legitimate, and that is to put in an I here. Okay, what's I? The identity, which is 1's down the diagonal, 0's everywhere else. Right? It doesn't change anything because it's like multiplying by 1. So when we write this out as A minus lambda I x equals 0, then this is now, these are both sides n by n, and it works. So we can subtract them, we can take the x out. Now why are we doing any of this? It's because we are going to try to figure out what x is. So we're going to solve for x in a system, just like if you're solving for x, y, z in a system of linear equations, we're going to do the same thing. We're going to solve for x. And usually when we solve a system of linear equations, when we solve a system of equations, we have ax equals b. We augment a with b, we row reduce, and the answers are x. So we need x separate from what we're going to solve. So we're going to actually set up a system here, but the system, instead of a, just a, it's going to be a minus lambda I augmented with 0. We're going to row reduce to solve for x. Okay, so it's the same as doing this. We forget about the x, because that's what we're trying to solve for. We augment a with b. We row reduce to solve for x. Here we're going to forget about x. We're going to row reduce this matrix. So it's a step before, because you actually have to find that matrix, and augmented with 0. All right, so what does this look like? So remember when you row reduced with a's in the matrix on that test 2? Same idea, but you're going to have lambdas in the matrix. So you have to row reduce with a letter in the matrix, okay? Because we don't know what lambda is until we find the eigenvector, and then we'll be able to find that, right? And actually we'll find the eigenvalue, and then we can find the vector from that too. So, steps 1, A is a square matrix. Find A minus lambda I. Two, we'll write the steps and then we'll follow them after. Find the determinant of A minus lambda I. This will have lambdas in it. Oh yes, we're not going to row reduce right here. So this will have lambdas in it. It will be a polynomial. Called the characteristic polynomial. So I underlined it because that's an important word. I could say find the characteristic polynomial, and you have to go through all these steps to do that. Find A minus lambda I, find the determinant of that, and that would be the characteristic polynomial. 3, solve the determinant of A minus lambda I equals 0 for lambda. And these will be your eigenvalues. 4, solve A minus lambda I x equals 0 for each eigenvalue. This will be the eigenspace. So, and the reason it'll be the eigenspace, when we solve a system of equations, and you get infinitely many solutions, that means there's more than just one vector, like t times a vector. When we solve a system of equations, we get infinitely many solutions. This will give infinitely many solutions. All of the vectors together with that t in front of it, the parameter, when we write it in parametric form, that is the eigenspace. If we write one example vector in that space, that's the eigenvector. Okay, so you can list as many eigenvectors as you want once you found this solution. Okay, so we're going to go through this, and we'll start with a 2 by 2. Okay. So step 1. Find the matrix A minus lambda I. Okay, so this shouldn't look too hard. I is the identity. It's the same size. Stick a lambda in front of it. If we were to calculate this, put that minus lambda, multiply it in, and then we add them. So 1 minus lambda, 4 and 0, 2 and 0, and 3 minus lambda. Now, I want you to look at the original A, and look at what A minus lambda I is. What did we do to A? What's different about these?
Minus lambda down the diagonal.
Right, minus lambda down the diagonal. So that's really all you need to do. A minus lambda I takes A, and we need to subtract lambda from the diagonal. Do you see it? So you don't actually need to recalculate this every time. You just do minus lambda down the diagonal. Now we want to find the determinant of that. So the determinant of A minus lambda I. So a 2 by 2 is easy enough. Multiply the diagonal and subtract the backwards. So if we work this out, there it is. So it gives you a polynomial. Now, you don't always want to multiply that out because you do need to factor it. And when it's a 3 by 3, you're going to have a cube in here. Do you remember how to do polynomial long division? Anyone remember, or synthetic division? Okay, so you might want to look that up. I could probably make a little video and put it up there for you, okay? So it probably won't take me very long. So do you know what I mean, polynomial long division? When you have to factor a cube, or if we did a 4 by 4, it would be a 4th power polynomial, but I don't make you do the determinant of a 4 by 4, so, yeah. Okay, so this, though, is called the characteristic polynomial. So sometimes you're just asked for the characteristic polynomial, and that would be it. You would stop. Okay. So, and then the next step, once we find the determinant, is to set it equal to 0 and solve for lambda, and that will give you your eigenvalues. So the next step would be lambda squared minus 4 lambda minus 5 equals 0. Five and 1 minus 5 plus 1. So there's our two So this particular matrix A has two eigenvalues, 5 and minus 1. Okay. They can have, like if you had to use a quadratic equation, they could have a root in them. Like that's legitimate, but it makes calculations kind of hard, so I just avoid that. But it's not that they don't exist. Like they don't have to be nice numbers. And in the next section, we're going to do complex numbers, and we're going to go back, and they can actually be complex numbers. And then we have to row reduce with i's in our matrix. Okay, so we're just going to see ones that work nice for now. So those are our eigenvalues. Now, to find the eigenspace, you take each one, and you have to row reduce a separate matrix for each one. Okay. So, to find the eigenspace, which is just the set of all possible vectors, let's start with lambda equals 5. Okay, so we have to do it for each. So what we do is we take our A minus lambda I, and that matrix, and plug the 5 into it, and get that matrix. So this was 1 minus lambda, 4, 2, and 3 minus lambda. You're just plugging the 5 in for lambda. You get a new matrix. Okay. So this will be 1 minus 5 is minus 4, and 3 minus 5, minus 2. Do you see that the two rows are multiples of each other? Yeah. Remember, it always has infinitely many solutions, so that's going to happen. Okay? If you don't get infinitely many solutions, you messed up. Okay? Yeah, Eigen, yeah. It comes from someone's name, probably whoever invented this. So where on earth do we use this stuff? Well, it's actually for transformations. It's like if a matrix corresponds to certain points in space and you want something to happen to it, maybe you want them to be steeper, slanted, so then you can multiply by an eigenvector that will do that to the matrix. Yeah. Or maybe you want a rotation, you want all the points to flip down and be the other direction, then there's another eigenvector that would do that. So it's used in engineering. We don't do the applications for it, but
For area and volume as well.
oh, absolutely, yeah. Yeah, so there's lots of things. Eigenvectors and do come up in different applications. Okay, so what do we do with this? We plug the 5 in, then we row reduce. So, to row reduce, make a 1. So, row 1, it'll be row 1 divided by minus 4. If you're really good at row reducing, you can jump right to the answer. So, we need a 0 here, that's in row 2. So, minus 2, row 1, plus row 2. Because that's a 2, that would need to be a minus 2. When we do that, we end up with this. So, we've got we can't row reduce further because you can't make a 1 in this bottom row. So we write out our solutions. So this is x and y. So x minus y equals 0. Remember, y would be our free variable, and here's our lead. Right, so we're going to let y equal t. So this will be x is equal to y, and y is t. So x equals t, y equals t. Yeah. Write it in vector form. So that's parametric form. But we want it in vector form. So that would be vector x is t times, if we factor out the t, 1, 1. So our eigenspace is this, there's different ways to write it. You could say is t times 1, 1. because that's a set of all vectors. But usually you would put, to make it a real space, put it in curly brackets. That's how you'd see it anywhere. T times 1, 1, and T can be any number. So that would be the set of all vectors, the eigenspace. The eigenvector would be what? 1, 1, or 2, 2, or 3, 3, or 100, 100. It doesn't matter which one, but usually we just take the one that's there and say that would be an example of the eigenvector. But it could be any multiple of that. They're all eigenvectors. Just as long as you don't put 0, 0. Okay, so they're all eigenvectors for that eigenvalue. So how could we check that we did it right? How could we check it? Well, we did that as the first question. If you do A times X, you should get lambda times X. Right, so if we take our original A, which was 1, 4, 2, 3, multiply it by X, 1, 1. We get 5, 5. And then you do the same thing for the other eigenvalue. So the other eigenvalue is -1, I believe. Yep, -1. So you take your A minus lambda I, you're going to plug your -1 in. So this will be 2, 4, 2, 4. And like I said, it's always going to be multiple. If it's not, you mess something up. So it always has to have infinitely many solutions. So then we row reduce. Divided by 2. We could do this one at the same time. Row 2 is minus row 1 plus row 2. Or do it in separate steps, it doesn't matter. 1, 2, 0, and this would be 0. Any row, once you make a 0, and it's the same row as the first one, they'll cancel out. Okay, so when you row reduce, you get this. And so we write out our solution. X plus 2y equals 0. So x equals minus 2y, and y is t. So x equals minus 2t, and y is just t. So our eigenspace, factor out the t, minus 2 and 1. And an eigenvector. Or any multiple of that. So in fact, if I end up with fractions in my eigenspace, I will just do a multiple. Like if there was a 1/2 in it, I would multiply it by 2 to get rid of the fraction, because we're going to have to use these for something else after, and it's better if they don't have fractions in them. So you can use a better vector in the space if you want. You don't have to use that one. Right? And then you could check, of course, by multiplying A times X. So minus 2 plus 4 and minus 4 plus 3. which is right, because lambda was 1. Right. Oh, minus 1, and that is minus 1. Good. Opposite signs. Yep. Yep.
You just mentioned that eigenvector cannot be zero vector,
Right.
but you actually give
Oh.
all real numbers, so t equals to 0.
Yeah, so you could say that. I don't know, they don't actually usually say that. But 0, 0 is not an eigenvector,
But it's in eigen.
but it would be in the eigenspace. I'll have to look that up, why they don't do that, because I know for sure they don't say t can't be 0. I've never seen that, and that does make sense, but I'm sure that 0, 0 is not an eigenvector, and I'm sure that they don't write t is not 0. So I'll just double check that. If it doesn't say it in the book, I'll ask someone else. And I might think of the reason why in a minute. Okay, so how many minutes was that? Okay, so let's stop here, and then we'll do a 3 by 3 in the next video.